All right, so here we're going to do this. This is the Big Bang and Galaxy Notes. It's introduction. Um, you will probably have to do some reading along with this on your own. So let's just get in and get started. What is the Big Bang Theory? This is not the TV show, although that's very funny and has some science in it. The Big Bang Theory states that the universe began as a cosmic explosion. So basically, a giant explosion in space, but happened from one singularity, like one tiny pinpoint of space. Scientists theorize that this happened. The time frames vary anywhere from 14 to 16 billion years ago. So we in our class will just go with the middle ground and say 15 billion years ago. This is also seen as BYA sometimes. So this is a graphic representation of how it may have looked, and I put quotation marks around it because it's a theory. We can't go back in time and prove that it happened, so this is all based on science. So in the beginning, there was a huge explosion, and if you look at the timeline, that is 10 to the negative 43 seconds. So that means it is like 43 zeros after a decimal point, and then the number one. So this is super, super fast, like that. Um, but when this happened, it happened very, very quickly. If you look at the second installation of time, we start to see temperature really, really hot, which excited all of the atoms and the structures. The third placement or the third time frame, if you look the orange area, we see protons and neutrons begin to form, and there's a cooling effect that happens, so they start to lump together. And then there's the fourth time frame, which is actually 1 second in between there. So you can see all of the creation of electrons, quarks, neutrons, and protons all happened before 1 second mark had happened. The fourth time frame, we get hydrogen molecules or atoms pushed together, and then as the nucleus itself gets heated high enough, it forms into helium nuclei. At the fifth mark, we see electrons combining with the nucleuses of the two atoms mentioned, so we actually get atomic structure like what we see now. It also begins to start to cool even more. And then you see at the sixth mark, this is the 10 billion years ago marking. This is where gravity starts to pull hydrogen and helium together. It collects or coalesces, that's that C word there, into giant clouds. They start to look kind of like the swirls in the picture. Gravity becomes the central part to making the turn happen in most of our galaxies. And then the 15 billion year ago mark, we see galaxy clusters, much like we see today. There are a few stars that begin to die out because their hydrogen and helium atoms within the star burn so very quickly. So one of the things that supports this theory is this background radiation. This states, this finding, this background radiation is left over from this explosion that happened. So it would be constant through that entire picture. As it spread throughout the universe, it spread really evenly and it's very constant. There's no place where it's not there. So the scientists theorize that it must have all happened at the same point because it's evenly mixed through the universe. Uh, these are some pictures with it. This Wilkinson probe it's in the picture, it's that kind of gold looking thing at the top, and it goes and takes pictures and kind of spins in circles and takes these radiation pictures. So the center picture is the actual radio frequencies and how, if you look, they're very similar and they're not jumbled. There's an evenness to it. There's pockets where there's more gamma radiation, but if you were to look, that's actually where there's pockets of different stars. If you look on the left-hand side, that is like a sideways view of our galaxy, and so you can see where the red cluster is where the gamma or the stars are located, and then the green is the radiation that's left out. So this is the microwave radiation. Remember back to when we talked about the EM spectrum. This is a step up in frequency from the radio. And you can see that it's pretty evenly dispersed in the center where most of the stars are located. This is again looking kind of sideways at it. So you're looking, the middle part would be where all the stars are, and then up and down above it. So after the Big Bang happened, gravity started to affect particles. Remember particles from when we talked about chemistry? Really differently. Where they were racing in all kinds of crazy directions, gravity starts to pull them together into what we call clumps. There's a sciencey word for it, but most scientists refer to it as clumps of particles. As these clumps get pushed together, they get pushed into clusters of matter. So what was just kind of random particles of hydrogen and helium nuclei get smushed together into making actual atomic structures because the racing protons get pulled into the gravity. And then over time, these clumps of matter become those swirling clouds of gases that would then become galaxies within the universe. So galaxies seem to be moving away from Earth, and Earth is our focal point because that's where we are, so that's where we look from. After looking at the galaxies move away from us, they seem to give off kind of a red tint when they move away. So that tells us that the wavelengths between us and the galaxies are getting farther apart. The things moving towards us, if we turn the other way and we look at how things would be moving with us, if they move towards us, then they tend to give off this kind of blue tint or light, which shows that the wavelength is getting smaller. So this works if you think back to when we did visible light. The red wavelengths are longer than the blue wavelengths. So as galaxies move either towards us or away from us, you can see in the picture at the bottom on the right, the star that's moving away from us gives off a red tint, while the star that's moving towards us gives off a blue tint. Now they use a sun in this picture. Our sun is not moving away from us to give a red or a blue, but they use it because it's easy for us to recognize as a star. So just another visual. This shows a distant star and an unseen planet. This is just one more way to look at it. So if these pictures don't make sense to you, then you can, pause it and draw one of these. The expanding universe. Again, if this theory is true, then the universe is in fact expanding and it's getting larger every day. And the objects nearer to the edge would be the oldest. If you think about when you pour something out on the concrete, like if you've ever poured soda on the concrete, the first pour pushes away towards the outer edges, and the newest soda that hits the ground is coming straight from the center part where you poured. The most distant known object to Earth is 12 billion light years away. And remember, light year is not an actual time, it's a distance traveled over time. So we know that if it takes 12 billion years for the light from that object to get to us, that it is at least that many years away. So it's 12 billion years away from us. So that kind of gives us a reference point that if the Big Bang were to have really been true, then we can judge things based on how old they are from us. So this is a visual, basically what we just talked about. So at the beginning of the bottom, the singularity, that's the point of reference for everything. As it explodes outwards, we get those mass and clumps of particles. And then we start to get defined galaxies. And then the galaxies that are defined start to move apart. So the support for these theories, and these are the parts that will be important for the test to remember. The supports are the presence of background radiation and the observation that things are moving away from the center part of the universe. So this would be the redshift and blueshift concepts. So then, because this is science, we have to focus on a theory versus a law. A theory is a summarized hypothesis or a group of hypotheses that have been supported with repeated testing. It's a theory because there's no other evidence to prove it wrong or dispute it. They can't fully prove that it's truth and always going to be that way, but it's the most widely accepted answer for the proposed question. whereas a law is a generalized body of observations that at the time it's made has no exceptions that can be found. So this is the one that's truth. It's proven time and time again. They can see its beginning and its end. Scientific law explains things, but it doesn't describe things. A theory usually describes the stuff that's happening. So then I think this is our last slide. This is your vocab for the week. It's Big Bang, background radiation, gravitational pull, and then redshift and blue shift. And yes, you can go back into the video and pull information from it, but I hope you will go and look for more detailed explanations for your words. So yeah, there we go. I hope to see you around in the hallway, and take it easy.